Here in Greenland are some of the oldest exposed rocks ever to have been found. And one belt of rock may take us back as far as we can go in the long history of this planet's existence. Dr. Minnick Rosing of the Geological Museum of Copenhagen has visited Greenland many times in his research for evidence of Earth's early history. This is a layer of fossilized carbon which he believes might be the earliest evidence of life. Under the microscope, tiny black grains can be seen. These possibly are grains of carbon, the building blocks of life. If so, there may have been tiny microorganisms drifting in the water that were alive, taking in nutrients, reproducing, and then dying and dropping slowly to the ocean floor. When the carbon was deposited those billions of years ago, the thin straight lines on the rock show it was undisturbed, proof that this was the bottom of a deep ocean, and the thickness indicates that already life was plentiful.
When the oceans formed and the conditions for life were present, life could have emerged at that time. And definitely by 3.8 billion years ago, life had reached the level of sophistication that allowed it to live in the water and produce a lot of carbon. So it was highly advanced life at this time.
For these microorganisms, the prerogative was simply to survive. Now there is the strong likelihood that life, despite the odds, has survived. But how could that be possible? With the oceans gone, where could life have found a sanctuary from the searing heat? A clue to the answer was found in salt. These salt lakes in the American Southwest are the remnants of an ancient sea. Millions of years ago, in the Permian era, the upheaval of the bedrock drained the oceans and left behind these lakes. Dr. Russell Vreeland is a microbiologist based at Westchester University. He's been studying the survival strategies of microbes and has come up with some remarkable results. To him, these crystals are as valuable as any gemstone. Inside the crystal are minute droplets of the seawater trapped within as the salt crystallized. A tiny hole was drilled so that the drop of water could be released. Perfectly shaped microorganisms named Bacillus permians were found, relics from the past. But the next finding was truly extraordinary. For 4 months, the microbes were fed with a nutrient broth. They began to divide, then multiply vigorously. After slumbering through tens of millions of years, they had come awake.
Bacterium that we found in the crystal was neither alive nor dead. It was in a state of long-term suspended animation. As a spore, it just literally could do nothing but sit and wait. Amazing part about a dormancy like that is that they don't need nutrients, they don't produce waste product, and they have the ability to just sit and wait until conditions are favorable again for survival.
Yet it seems that life did exactly that. It survived.
I find amazing is life is really tenacious. And once it came about, once it evolved, once it was on this planet, it would have taken a huge event to sterilize the planet. You would have had to heat the planet literally all over and as deep as you possibly could, virtually melt the planet to really destroy the life.
Dr. Sleep of Stanford University looked long and hard at early life's survival capabilities. He thinks that he's found an answer. There was a part of the Earth where life could sustain itself, and this was deep below the ocean floor. This graph shows the temperature distribution in the subsurface of the Earth. The red area is the heat from the Earth's core. Nothing can survive in this region. Green are regions below boiling point. Blue are regions just below 50 degrees Celsius or 122 Fahrenheit. Life could survive in the blue zone, the Goldilocks zone, as Dr. Sleep calls it. This is one of the deepest man-made shafts in the world.
Geology. Luckily, with a lot of rock from the sky.
Dr. Esther van Heerden of South Africa's Free State University is researching the survival of life deep within the Earth. Her findings and those of the research team are astounding. Groundwater is seeping from the rocks, and the surface of the mine wall is covered by a thick film of white and black. This is a mat of various forms of bacteria, species not found on the Earth's surface. Here they do not use oxygen, they are anaerobic. But research shows that many of them still possess the genes for oxygen respiration, useless down here. Perhaps this is evidence that these microorganisms once lived on the surface, only to migrate to these depths, perhaps to escape the heat of a total evaporation impact.